Hi, this is Group 13, formed by Jorge Bulnes, Paola Londono, and Ryan Penland from Computer Engineering, and Dylan Rivera from Electrical Engineering. Our project is the self-propelled robotic car with voice command and object recognition. There are many types of robotic devices that are self-driven. We know the Roomba vacuum that is so popular in thousands of households for its ability to move around, collecting trash from the floor. There are cars just like the one in the picture, created with the idea of, for example, avoiding most car-related accidents. There are also devices like self-driven lawnmower, so you don't have to do the work. Many self-driven devices have been commercialized and have the capacity for path rerouting or obstacle avoidance. Now, adding a voice command to these self-driven cars is a great feature that allows the car to move and take directions from someone speaking to it. The examples show some projects that have been created to demonstrate how both features interact together. The three projects are very simple, requiring just an Arduino as their microcontroller. We can see these types of projects have no commercial use as of yet, and they look more like prototypes or something that could be developed at a higher scale in the future. There are specialized robots right now with this combined capacity, but they are expensive and for more specific use. What our group would like to show you today is the work we've been doing combining obstacle avoidance on a self-driven car with voice command and object recognition. There are visual language navigation or VLN projects, and most of them are in the research stage, but there are not too many instances of the combination of these three elements. Being able to combine these features could be the beginning of how a visually impaired person sitting in a living room could have a walker left by the main door brought back to him or her, or someone that just had surgery could ask a robot to find his or her cell phone and bring it back to the bed. There are many possibilities. Our main goal is to build a functioning self-driven robotic car that can move front, back, left, and right with the capability of following a basic and specific voice command related to directions, and that asks about finding a target and locating it while avoiding any fixed obstacles in its path. We must successfully apply machine learning and algorithms to be able to achieve our results. Our basic goals are more specific to the different stages of the project. So first, we want to be able to build a program and a robotic car able to move in different directions and recognize obstacles by stopping and avoiding them with the use of distance sensors. Second, our car should be able to recognize simple voice commands related to direction. For example, move forward, stop, turn left, etc., from a pre-programmed list. Third, the car will be able to take a voice command to locate a pre-programmed object. Fourth, using a camera, the car will locate the object that was requested to be located. Since this project can be a foundation for many things to come, there are many long-term stretch goals that our team would like to achieve, but here we're presenting the ones that could be incorporated into the project if we had additional time before the end of this semester. First, we would like to incorporate VLN technology that can be to avoid dynamic obstacles in a more complex environment. Second, add a user interface display to make it easier for the user to turn command mode on and off, as well as for additional features. Third, add a special sound to the robot that indicates that it has reached the goal of finding the expected object. The sound could be in the form of a sentence, a part of a song, a beep, etc. And fourth, add an LED light or LED lights to show the user when the robot is turning to one side or the other or stopping, etc. Now, going through specifications and requirements is how we figure out exactly what we needed to investigate in order to create our project. To find our specifications and requirements, first we ask ourselves what will make it a great product. We came up with the marketing requirements from this. So the ones we got were low cost, low power consumption, small surface dimension, great visual quality, easy to transport, safe to use, and excellent voice recognition. From there, our engineering requirements became first, the cost should be less than 800 because that's the budget that UCF is allowing us to use for the project. Second, it occupies an area of less than 225 square inches, which is pretty much 15 inches wide by 15 inches long, making it easier to move in narrower places. For the camera quality, we want a minimum of 1080 because there are fewer image detection errors this way. For the microphone, we want one able to connect to at least one available voice-to-text processor to facilitate this part of the project. Regarding the distance sensors, we wanted something able to locate an obstacle at least 4 feet away. We want to make sure that the robot can turn away from the obstacle when it's 1 foot away, and this is actually something that we consider to get it closer to the obstacle once we test it. Finally, we want to keep the car light, less than 5 pounds, and this is to allow us to use cheaper parts and less power.
So this is our block diagram for the hardware aspect of the project. So at the top, we can see the power supply that is followed by the form of the battery management, as well as the input and the outputs of the system for the wheels and the motors. Then we can see how it follows all the way to the ultrasonic sensors. So we are using our own version of Arduino. So basically, we are creating our own Arduino microcontroller to make some of the functionalities possible. Although uh, basically this section is mostly being directed by Paola and Dylan. Everyone has been keeping track of all the different components of the hardware diagram. So our version of the Arduino connects directly to the brain of this project, which is the Jetson Nano. Then we have the microphone and the camera directly connected to the Jetson Nano. And Ryan has been the person that has been mostly dedicated to the object recognition section. And myself, I've been working on the voice command aspect, the voice section of the recognition and the commands. But as mentioned before, everyone has been really involved in this project. Regarding the software block diagram, so we will be using the Jetpack, which is the Jetson Nano software. The good thing about it is that this allows to integrate the libraries needed to program our robot, including the implementation of the algorithm for the voice to text and image to text, which are pretty crucial for this part of the project. On the right side of the diagram, you can see how this whole software points to and from the simulation, since we are using the simulation to test pins and code while the PCB and all the parts finish arriving, which has been a little bit stressful, but we have managed so far. This also shows the relation with the communication and the integration that are primarily the embedded aspects of the project. So this part we make sure that the input devices are properly connected and working so we have a successful output. For the system design diagram, there are two main things that are going on with our car function. Once we switch our car on, and we have the choice of giving a voice command with a direction to follow. For example, we would ask you to move forward, turn left, right, or stop, the basic functions. Then the car will move following these commands, and if it finds an obstacle on the way, the car would stop. At this point, we can provide another direction command or move the other type of command, which is the object recognition aspect. So for this, the command would be something like find the red ball or the yellow teddy bear, and the car will proceed to move forward. And if there is an obstacle in the way, it will be turning right, left, or it will go backwards if it's necessary. Once the object is recognized, the car will provide a signal, or right now we're discussing if it should provide a signal or a sound, or if it should call out the name of the object out loud. For the system design approach, so here is basically laid out how the car system is working. So for the first floor, we're going to have the sensors, the DC motors, and the batteries, plus the PCB. On the second floor, we're going to have the Jetson Nano, and for the third floor, we're going to have the camera and the microphone. So here we can visualize the bottom of the chassis, how we have the two DC motors, and you can see the actual measurements for the bottom of the chassis. And on the right side, you can see the top of the chassis. So we're gonna have three ultrasonic sensors. Uh, Behind that, we're gonna have the motor driver, we're gonna have the power management, and we're gonna have the two 3.7 volt Leon batteries. On the second floor, we're gonna have the Jetson Nano and the fan. We think that this location is crucial as of now because we think it's a great place to put a lot of the weight since he's gonna balance out the robot. We don't want to put it on the bottom or on the top because we don't want to make it too unstable. On the bottom, it might be stable, but as of now, this design works. So we're gonna have to further test in order to see if it's completely going to work like that. And on the third level, we're gonna put the camera and the microphone, which are not that heavy. They're pretty light, and we can take advantage of that since it's not gonna have stabilization issues with the components.
So our PCB block diagram will be, we will have a input connector, which we will connect the batteries. We would then go from there to two mega chips, and from these mega chips, we would have three sensors, and these three sensors will each have their own connector in the PCB. And then we also have a DC motor drive, which is an L293D chip. And from these chips, we would have some two extra connectors for the DC motors. So each component will have its own connector on the PCB, so it's easier for us to handle. And yeah, so on our PCB design approach, we the main function our PCB must accomplish is to power on our motors and control our sensors in order to obstacle avoid. We will have three ultrasonic sensors and two motors connected to it, and our PCB has a power stage with our main source being two 3.7 volt lithium ion batteries. Then we will go through our circuit powering two mega chips, and these will control our sensors and send commands to measure distance. This will be connected to a DC motor drive L293D chip that will be connected to our DC motors. Now I will show what we have for our PCB design, and for this we use Altium Designer. We use Altium Designer because this is a PCB and electronic design automation software package for printed circuit boards, and which is easy and effective to use. In the time I've used it, it's pretty straightforward. Um, to make sure the connections are correct, we use Altium to validate schematic and make sure there are no technical errors. And also, we have simulated the connections with the code of the actual components. So basically, our PCB will go through three stages, which are the power stage. And the power stage will be controlled by some integrated circuit operational amplifier and integrated circuit voltage regulators. The next stage will be the sensing stage. The sensing stage will be controlled by two ATmega chips, which will handle the code. And the last stage will be the DC motor stage, which will be controlled by the L293D chip. The most significant component decision in our PCB are, of course, the ATmega chips and the L293D chip because they are in charge of the most important functions in our circuit.
For the significant component decisions, we decided to go with the Jetson Nano 4 GB developer kit. It has the ability to handle machine learning, which is a really important part of a project. It comes with a quad-core Cortex A57 processor, a 128-core Maxwell GPU, and a 4 GB LPDDR memory that helps the machine learning happen. It also comes with the ability to connect a camera and a microphone. And this works so well because it comes with a 16 gigabyte eMMC NAND flash memory, which is the ones that you're gonna find on USBs or SD cards or on SSDs. These can provide faster data transfer rates, which is important for the machine learning part, and it has quick access to large amounts of data. It also contains a lot of resources online, and this can come really handy when we get further into our project. For the other significant component that we chose, one was the XBF 3000 root speaker. So the good thing about this speaker is that it has far field voice capture. It contains four microphones array, so it can basically capture a 360-degree angle of sound. It comes with 12 LED lights, which as of now they're not that important. And the chip contains the speech algorithms that we need for the machine learning. It has voice activity detection, so if we choose to wake up the robot with certain word, we can do that. And it has noise suppression, and acoustic echo cancellation. For the Arducam, this was a pretty small camera. It's pretty convenient, and it contains a frame rate of 30 frames per second of 1920 by 1080, and it has a dynamic range of 80 decibels, and plus a 160 field of view. It has an integral IR filter, and it can capture image all the way up to 19 feet apart from each. For the significant design decisions, we decided that it needs to be able to rotate 360 degrees without constant pivoting. It's really important that it has a continuous rotation. It needs to have a pre-trained English language installed on the microcontroller. Since many of our group members are Spanish speaking, it will be pretty interesting to see how it works with Spanish, but the priority is in English as of now. And it has three HCSR04 sensors on the front of the vehicle that are gonna be really crucial to avoid obstacles and analyze our surroundings.
There are many constraints to keep in mind, like economic, environmental, social, political, ethical, health and safety, manufacturability, time, and sustainability. I would like to emphasize on two of the most important ones for us, which are first, economic. Economic constraints for this project are many. I'll start by discussing probably the most expensive part of this project. The Jetson Nano happens to be the most expensive part of the robot since microcontrollers and microcomputers are not that abundant right now. This problem arises from chips that are underproduced, and the demand for these types of devices has risen in the last years, specifically since the pandemic started. We had to choose the cheapest one that will help us achieve our goal because different companies produce the Jetson Nano, like Nvidia and Jaboom. Also choosing between the cheapest but best solution for our microphone, camera, and sensor. In general, economic constraint is important because we might not have chosen the best option to accomplish certain tasks because of the price. Another important constraint for us is time constraint. One of the most important aspects is to balance time in life. How to organize our time is important if we want to complete this project. We have to understand that we are working as a group and that if we don't make enough time to work on the project, not only will we fail, but also our team members will. This is why we must work together as a team and try to organize our time when we meet together and try to be effective. We have to communicate tasks well and organize so that we never waste any time since it is essential, especially when working with such extensive tasks. Time constraints could affect our end result if it is not managed effectively.
For the standards, there are three main standards that we have to take into consideration. First is the related standards that has the USB, the impact of the USB on the design and the camera serial interface, plus the impact of the CSI on the design. For the communication standards, we have a table that is comparing the protocol, the frequency, the channel width, and the theoretical max data rate. And finally, for the safety standards, we include the braking system, awareness barrier devices, audible and visible warning systems, and finally, the control devices. For the USB, we need to have a connection between the protocol and the electrical layer that will be implemented by the microcontroller. This communication protocol is widely used in many electronic devices in the world, and it's important to have it. The impact of the USB on the design needs to be required in a form that the connection between the camera and the microcontroller is going to have the largest impact on the USB. It was really important to make sure that the microcontroller selection will feature a USB input so we can get information and extract that data from the external camera and it can be able to process it. For the camera serial interface, we have another communication protocol that is used globally by many companies. Is the CSI, or it can be CSI2, CSI3, and the CSS. The impact of the CSI on the design is that the product will be steady and it's going to have a steady connection between the camera and the microcontroller. For the communication standards, you can see a comparison right here of the protocol, the frequency, the channel width, and the theoretical max data rate. So for the protocol, it is formed by a series of half duplexes. It uses a CSMA or slash CA, depending on how you want to call it. And the Jetson Nano microcontroller has that capability of using the M2 key. This is an adapter and pinouts that have standard specifications defined by the PCI SIG document. They are created to be used in platforms supporting NXP, Wi-Fi, Bluetooth, and all these frequencies and channels that may vary depending on what you need to use. And finally, for the safety standards, this is a really important part that we focus a lot of time to potentially see some of the safety things that we need to take into consideration. So for the braking system, we apply an emergency button that will allow the robot to brake. We wanted to do this because we don't want the robot to shut down in case it was doing some instruction. We don't want the process to start all over again. So we think this is a good method to just uh, cut off the robot at any time. Then we have the awareness barrier devices, which is important to the robot so it can alert when a person is near it. We could use a system that can benefit, humans like warning cones, but to make sure that people are aware that they're not surrounding the area. We want to have some cones, and we want the robot to be able to identify the cone so it can avoid those obstacles. For the audible and visible warning systems, we're going to be using a sound or a light that is going to emit like a warning sound. This is going to alert people of the presence of the robot on their way. This is especially when it's navigating. So we decided to have a pretty much an installation of LED lights as a safety measure. And finally, we have the control devices. So for this part, we have a couple of the OSHA points that they want to consider when you're considering a control device. These include the main control panel that is outside of the robot. It has also the automatic stop capability, which is provided by the stop button. It also controls and activates the systems that are guarded against accidental operation. We want to have also user prompt displays that are used to minimize human error. We have also a separate breaker that can be logged in off just as a final safety measure. And the robot is being installed due to the manufacturing safety guidelines. We're not experimenting outside of the safety guidelines. We also want the power conforms to the specifications, and we want the road to be secure and stable.
So for our project successes, first and foremost, I would like to highlight the importance of a well-designed project plan. It really lays the foundation for a successful project outcome and enables us to achieve our goals efficiently. In this project, we really took the time to carefully plan out each stage of our development, and we considered all necessary factors such as our resources, our timeline, and our budget. As a result, so far, designing and implementing the vehicle portion of the robot has been very successful. We've been able to meet all of our goals to this point within our specified time and budget constraints. The project design has also allowed us to efficiently manage our resources, ensuring that we're making the most of what's available to use. We've also begun working with our TensorFlow, getting that environment up and running, and that has been a critical part of this project. This involves installing and configuring all of our necessary software tools, libraries, and dependencies. Right now, we've actually been able to get to working with models that have been pre-configured with voice and object recognition, and we have begun being able to figure out how to start modeling on our own. So for the difficulties of the project, getting the Jetson Nano microcontroller able to function properly has been kind of a difficulty, but we have overcome that. It's because the Jetson Nano works primarily off of a Linux-based system, and as we all have probably Macs and Windows, it's very difficult to get it formatted and set up properly so that we can begin working on it. And as a result, implementing and integrating software to the microcontroller itself has been quite a problem. But we have been actively looking for solutions, and we have made great progress in that aspect. In terms of the project budgeting and finances, we were given our budget by the ECE department at UCF, and the budget given by our department has covered up to $800, and every single part we've had to this point has been covered by that budget. Right now, here's our current expenses. We have the Jetson Nano microcontroller. We have our microphone, our ultrasonic sensor. We have 3 cameras. We have our wireless component, our chassis, wheels and motors, LED lights that will go on the car for testing. We are going to be using lithium-ion batteries. We have our motor driver and power adapter. And we have multiple in some areas of the budget due to in case if there's any faults. So for our current progress right now, this is what the vehicle looks like. Right now we have our sensors properly connected, and we have our wheels attached to the motor drive, and those are all attached to the chassis right now. Right now the sensors have been tested, the wheels have been tested, the motor has been tested, everything's been working great. We're slowly beginning to implement the software and getting that all hooked up to the chassis. And then as also alongside that, we are using a simulation software to be able to test our pin connections and develop initial testing code. Right now, this is what we are looking like in terms of our progress. We should have, we have the PCB complete this weekend, or during the week next week, and then we're going to begin testing our hardware and software, and then we'll begin building and unifying all of our parts so that we can have it done for the midterm demo. And then after that, it's going to be a lot of bug fixing and making sure everything's running efficiently and that we have no hiccups so that the final project can be complete by that April 17th date. And here are our references.